Let's do problem 2. In problem 2, we've got two people, and they start at certain places, and they're moving at certain speeds in certain directions. So person A starts here, moves 2 meters a second at a 45-degree angle that way. Person B starts here, moves at 3 meters per second at a 45-degree angle that way. And what we want to do is we want to use vector equations to describe their position over time. And the reason that's helpful is once you have their position represented as an equation, it makes it easier to answer other questions. Like if I wanted to know like at certain, like what's the angle between them at different times, or if I wanted to know like how fast is the distance between them changing as a function of time. And like all of these things are things that you'd ask in like physics or later on in calculus. So that's kind of, we're setting you up with the mathematical foundations for that. So let's go ahead and figure out how would you write a vector equation for that one's position. I'm going to call it A, and it's going to be a function of time. And using the pattern that we've been using before, I'm going to start with a position vector that points to where the starting place is, and I'm calling that P. So here, P is going to be the vector -5, 4. And now I know I want to add onto that the direction and the speed that they're moving. So it looks like they're moving at a 45-degree angle, so I know that the x component and the y component need to be the same. So for example, I could say t times like 1, 1. The problem with this, so this is like moving in the right direction. Here I'm saying start at this point, and then as time increases, I'm moving some distance along this vector. So either a short distance for a small time or a longer distance for a longer time. The problem is this is not moving at the right speed. And the way that you can know that is imagine plugging in time equals 0. At time equals 0, where am I? So I'm at -5, 4 plus 0 times this vector, which scales it, like shrinks it down to be a length of 0. So at time 0, I'm at -5, 4. Where am I 1 second later? Well, I start at 5, 4, but then I add 1 times this 1, 1 vector. So it means I've moved over 1 and up 1. So at time 1, I'd be at -4, 5. Okay, how far did I go? Well, I moved over, in that 1 second, I moved over 1 and up 1. So that's a distance of √2. And it took me 1 second to get there. So that's a speed of √2 meters per second. But I want to be going at 2 meters per second. So we have to do that thing that we looked at in class. I have to figure out what's a vector that's pointed in that same angle, 45-degree angle, but I want the hypotenuse to be a length of 2. Because I know that if the vector's hypotenuse is length 2, then that's exactly how far I'm going to go every single second, because I'm scaling that with time. Okay, so what's the scale factor I need? Right now, I've got a length of √2. I'm multiplying that by some mystery scale factor, and I want to end up with 2 in the end. Well, we'll just solve for the mystery scale factor by dividing by √2, and that gives us that our mystery scale factor is 2 over √2. So this is close. It doesn't quite work, but it's a good stepping stone to get us where we want to be. So now I can rewrite the vector as -5, 4 plus time times the scale factor that I solved for that's going to shrink it to be the length that I want it to be. And you could write it that way, or sometimes it's nice to simplify it, so I can multiply that in. So time times 2 over √2 by 2 over √2. Let's do the same thing a little bit faster for person B. So person B, their position vector starts at -3, -3. I'm going to add on to that time times a vector that's pointed in the direction I want. So let's see, -1, +1. Looks like it's going to take me in the direction that I want. But again, this is going at the wrong speed. This is going at a speed of √2 for the same reason that this one was. So I want this one to be moving at a speed of 3. So if I've got a hypotenuse of 2, sorry, if I've got a hypotenuse of root 2 and I want to rescale it so that it's length 3, I got to multiply it by some mystery scale factor, which is equal to 3 over root 2. So I can rewrite this as -3 plus time times the scale factor multiplied in. So -3 over root 2 by 3 over root 2. All right, so far so good. So I've got an equation for person A's position, and I've got an equation for person B's position. So the last part of the question asks, at a particular time, 1 minute later, at 60 seconds, where are these people? And what's a vector that describes the displacement from one to the other one? So just looking at this picture, I can sort of imagine A is going this way at a certain speed, B is going this way but sort of faster. So if I want to sort of make a rough sketch to help me imagine where they probably are, it's like B is going to be way up here somewhere, and A is probably going to be not as high up because A wasn't traveling as fast, and A is going to be way over here somewhere. And like I'm not even going to guess about what the values are. But imagining where they end up is going to tell me, so if I've got the position vector that's pointing to where A is at time 60, because remember my equation was the vector A as a function of time. So I'm plugging in time equals 60 to give me a particular vector that points to the position at that particular time. So this is my A vector. And what I'm saying is I would like to know what is the vector that points from A to B at that time. So A plus C should equal the B vector at time 60. So what could C be? Just like visually speaking, I can tell that the C vector should be the difference in the x coordinates as the x component, and the difference in the y coordinates as the y component. So let's do the computations. Those were the equations from the front page. Let's figure out what vector this points to at a particular time. So when time equals 60 seconds, I've got -5, 4, and then I've got a 60 here. But let's multiply the 60 in. So that 60 times 2 is going to give me 120. And then 60 times 2 gives me 120. And then, so this is telling me where I am as the sum of two different vectors, but I want to combine them together. So let's add the x parts and add the y parts. So that gives me -5 plus this, 120 over root 2. So that's the x component, and then the y component is 4 plus 120 over root 2. Okay, so those aren't like particularly nice numbers, but that does tell us where we are. What about B? So at 60 seconds, B is going to be at -3, -3, plus, so 60 times 3 is 180. So that's going to be -180 over root 2 and 180 over root 2. So same thing, we can combine them together. So the x component is -3 plus -180 over root 2. Here we've got for the y component, -3 plus 180 over root 2. All right, so there's a lot of writing, but like conceptually we're not doing anything complicated. So we've got an x position and a y position, an x position and a y position. So how do I know what to subtract from what? I said that this c vector that we're trying to find is like the difference in x's for its x component and the difference in y's for its y component. But do I do like the x part of A minus the x part of B, or do I do the x part of B minus the x part of A? Like you can think about it just kind of conceptually. If I'm going from A to B, as this arrow indicates, then I know that my change in x has to be negative because I'm headed to the left. So you can look at these two x values and you can say, all right, which order do I subtract them in to make sure that my change in x is negative? So you can think about it that way, which is totally fine. You can also think about this algebraically. So I said that a plus c needs to equal b. And think about what that means as vectors. I say follow vector a and then follow vector c, and those two added together should be the same as the vector that just points directly at b, because that's sort of like the definition of vector addition. So if we're trying to solve for c, that's the one we don't know, let's subtract a from both sides. So c must be b minus a. And that tells me the order that it makes sense to subtract the components in. So I can actually literally just write this out. I can say c equals the b vector, which is here. So negative 3 minus 180 over root 2 minus 3 plus 180 over root 2. So that's the b vector minus the a vector. And the a vector was negative 5 plus 120 over root 2. And then this is 4 plus 120 over root 2. All right, let's combine them together into one vector. So, I'll combine the x part of this one and the x part of that one, except now I'm subtracting. So it would be negative 3 minus 180 over root 2, that's the x part, minus this. So that means, so let's see, the opposite, so minus, it's the opposite of negative 5 is 5. So, well, I guess let's do it this way. Let's say minus, and then I'll put this in parentheses, and then we'll work out how the signs cancel in a second. So plus 120 over root 2. And then, we'll do the y part in just a minute. So how am I going to simplify this? Negative 3 minus the opposite of 5 is negative 3 plus 5. So that gives me 2. So I've combined those parts together now. And now I've got negative 180 over root 2 minus another 120 over root 2. So think about it this way. 180 over root 2 is like saying I've got 180 1 over root 2's, right? Oops. I've got 180 of whatever this number is. That's what that means. It's negative, but let's pretend it's not. What does this mean? It means I've got 120 of whatever this number is. So what happens if I add them together? I've got 180 of something plus 120 of something. It must be whatever 180 plus 120 is. So that's 300 of whatever that thing was. So that's a nice way of thinking about how to add, awkward numbers or numbers that feel awkward to you, as long as they're the same. I mean, you could also think about this as factoring, right? I'm going to factor out this common term, and then I add together those, and I end up with 300 times 1 over root 2. But since those were both negative, it's like I'm saying negative that much minus that much gives me negative that much. So 300 over root 2. Cool. So I simplified that. And then it's really just the exact same process for this one. And you have the answers already, so you can do that one on your own. As a side note, let me show you how you could... So I'm going to do the same process, but I'm going to show you how you could have done it without it being so messy. So here, something I'm noticing is... Here I could factor 2 out of both the x and the y, and here I could factor 3 out of both the x and the y. So if I wanted to, I could rewrite this as negative 5, 4 plus 2t times 1 over root 2, 1 over root 2. And here b could be negative 3 plus 3t over 1 over root 2. Oops, negative 1 over root 2, 1 over root 2. Okay, that's interesting. Remember that I want to find a plus c equals b. So that means c equals b minus a. So without doing anything further, let's just go ahead and do that subtraction right away. So a is going to be negative 5, 4 plus 2t 1 over root 2, 1 over root 2, minus b, which is -3, plus 3t times negative 1 over root 2, 1 over root 2. Okay, let's simplify. So I'm going to take this x part and subtract that x part. So let's see, -5 plus 3 gives us -2. Here I've got 4 minus 3, so that's 4 plus 3, 7. Wow, it's a terrible 7. Okay, so I've kind of covered this part and covered this part. Now let's look at this part. Here I've got 2t times 1 over root 2, and then I'm subtracting 3t times -1 over root 2. So these negatives cancel, so that's like 2t times 1 over root 2 plus 3t times 1 over root 2. So put those together, and that gives us 5t times 1 over root 2. All right. Let's do the y components. So this is 2t times 1 over root 2 minus 3t times 1 over root 2. So that's just negative t times 1 over root 2. And then I've still got the -2, there. All right. What was t? T was 60, right? All right. I think I'm not ready to have t be equal to 60, though. Let's combine these first. So I've got -2 plus 5t, 1 over root 2. And here I've got 7 minus t over root 2. Did that cover everything? Yeah, all right. And now I can plug in 60. So 60 times 5 is 300. And then, so this is 7 minus 60 over root 2. So I got the same numbers in the end, but this process was a little bit more straightforward because I postponed multiplying everything in, because that keeps my numbers kind of small, and it means that there's like less computation to do. So I just want to emphasize one more time that these problems might seem difficult because, like, look at how much is on my page here. But conceptually, what's happening is very, very, very simple. All I'm doing is adding and subtracting x components and y components. And if you think about it geometrically, it makes a lot of sense. I think the difficulty here is just procedural. It's just like being able to like wrangle numbers that have square roots of things. And like that's not the main goal here. You know, computers can do this stuff for you. The main goal is for you to kind of understand the concepts.